Everyone's tongue.
Well, then I feel like we'd really be the peanut gallery, you know? Cheering at.
In like an hour. So you're right.
I'll grab some pencils so I can chop it.
Yeah, chocolate grease or.
I was thinking of the band and like try Wizard when they drag the corpse. I was gonna mention that part. I'm thinking of the music.
People go try to pass it.
You could be the photographer. So like, just get up there like the entire time.
Test?
No.
Test. 1, 2, 3.
Yep.
I feel like you guys could hear me before, right? Like it was already.
It sounds different.
It's already okay?
It's for the online.
Yeah, the recording. Probably important
Right.
to be able to be heard.
Yes.
Well, as you pace back and forth, right?
Great. Testing. 1, 2, 3, and then John, I assume you're going to need.
We got that line mic?
Yeah, let me just.
We can use that for questions too.
Test. Oh, there it goes. Yep. All set. Thank you, sir.
Harsh falls over the ground. We're all waiting in anticipation.
I don't know why you shut up so early.
We were getting work done in the lab.
I'll do that search break.
Yeah, you're right.
We wanted to make sure we got the best seats. All or not.
I mean, I personally think the best seat is like right there.
Oh yes, but like.
What symbol is that? I do think it's crazy that we have like astrology symbols. Like, but obviously like here. It's facing
But that's your research, right?
astrology.
Is this the healing crystal workshop?
And I'm a specialist in cosmetology.
My mom makes that joke all the time.
The best encounter people on airplanes. It's like a myth.
I was once genuinely asked for an astropiece at the time.
Google it.
It's not like I like brush like it'd be really hard to like angle that like that.
I mean, if you think about it, metals are technically crystals. So, like, you are, like, resonating. That's all a waveguide is.
I mean, let's face it, X-rays do things to your body. I don't necessarily think that it's unusual.
Then you're gone.
Behave ourselves or anything, but the YouTube link is live, the audio is on.
Oh, okay, great. All right, the YouTube link is live, the audio is live.
So now what do we say?
How was the you said you were going to be setting up a YouTube channel.
It looks like there's a cat.
Oh, okay.
Yeah, accidentally. Oh, that's
You had to remind people like everything you wrote, but that you can't put the defense. Yeah, I don't know.
Yeah, what else would I get?
I can test, test. 1, 2, 3.
I think we'll have questions at the end. Tell the folks online that they can put questions in the chat
Okay.
at any time, but we'll cover them at the end.
Sounds great.
Unless somebody's got a burning question for as you're going, we'll try not to interrupt you too much.
Okay.
And your timing, you plan for,
I'm trying to leave 10 minutes at the end for questions.
so you're aiming for 50?
Yes. Well, that's assuming that we start right on time. But, yeah. Hello. What's that? Should I take my hat off? Okay, yeah, sorry. Oh, yeah. It's not something I ever thought about. Sweet.
Thanks, James. Okay, I think we should go ahead and get started. We're a couple of minutes past the hour, and I see that we've got the entire committee assembled here. Bill Holtzaffel from UC Berkeley is the external examiner for James's thesis, and he's confirmed that he's online and he can hear just fine. So I think we're all convened, and it's great to see so many here from the department, from the university, and from James's extended circle of family and friends come here for this event, this happy event. It's my honor to introduce James. James came to our group in 2016 as a new graduate student at that time and dived in with an amazing energy trying to understand all of the things that it takes to make a CMB telescope work, and really grabbed ownership of anything that was going on that was essential to the function of the project. Among the things I'll mention, he dived right into understanding the data quality and quickly became a mentor for the other students in our group who were scrutinizing that data quality weekly and became a teacher in that regard. He's went to the South Pole a number of times. I've lost track of exactly how many.
Same.
Excellent. A theme of James's research projects that struck me from the very start, the first summer that you joined us, you did the conceptual design for our next generation CMB telescope mount, the bicep array mount, a very complicated 3-axis mount that has bore set rotation needed to fit in very compactly for high performance CMB telescopes, receivers. You subsequently designed the hexapod that supported the mirror over that mount. You did an amazing analysis of the geometry of the four baffles and the ground shields, the sizes that those need to acquire to be able to intercept the rays that could communicate between our telescopes and the extremely warm Antarctic environment. All of which is really essential to the function of our telescope. And I noticed an interesting theme that there's a lot of geometry in those problems, and I think James...
It's kind of my shtick.
One of James's strengths is your approach to geometric problems. The thesis work that you're going to focus on in the talk today is one of the most important geometry problems in the universe. And so you'll tell us exactly how challenging that is, and we'll also come to appreciate how important that is. So over to you, James. And so this will go on until James stops. If there's a... we hope before the hour. So if there's a quick point of clarification, we can interrupt James as he goes. Otherwise, we'll take questions at the end from both those online and those who are here. And then we'll conclude the public lecture part of this thesis extravaganza. Okay.
Well, thank you so much, John. And thank you for the kind words. Can everybody hear me? Great, fantastic. So yeah, this has been a very challenging but also very rewarding experience. And it is with excitement to be able to stand before all of you today, where so many others have stood, and talk to you about my thesis, which is on constraining electromagnetic parity violation. Whoop, is this even on? This is on. Now it's on. Hello. Electromagnetic parity violation in something called the cosmic microwave background using another thing called the BICEP3 experiment. But before I get to that, I want to take a moment to thank everyone who has made this journey possible. First, I want to thank my committee members, Jim, Josh, Lincoln, and Bill, for their valuable feedback on my thesis and hopefully for their mercy in my private defense that's coming immediately after this. I also especially want to thank John for his advice and mentorship over the years. Something that was told to me by senior grad students in the lab is that when I was first starting out among the many things that John does well by his students, he first and foremost teaches them how to change their lens and to think and perceive the world as a scientist, and I think that is 100% true now. The way I think about the world and approach my research has drastically changed over the years, and I believe that my ability to do science and to do it well has all been influenced by John, so thank you. And then, of course, the next group I want to thank is the BICEP-Keck collaboration, of which I'm a part. It has been an absolute pleasure to work alongside such talented and kind individuals, and I literally wouldn't be able to work on such interesting science without their support. Not only has it been great doing science with these people, but I've developed some long-lasting friendships over the years through the work that we do. As John mentioned, we build our telescopes at the South Pole, which requires us to spend a non-trivial amount of our grad school careers in one of the harshest climates on the planet. And so despite all the long hours and the tough conditions, they've made it just a wonderful and memorable experience every single time I go. And so I'm deeply grateful for them. And then, of course, none of us would be anywhere close to where we are now without the loving support of our friends and family. So, and then lastly, I would like to make a special shout out to my wife, Brittany, who for more than a decade has provided the companionship and support that has allowed me to grow not just as a scientist but as a person. So thanks, sweets. All right, so let's talk about this thing. So what we're doing today is I'm going to tell you about how we constrain or measure electromagnetic parity violation in the cosmic microwave background using BICEP3. So, and my goal for the next hour is to explain to you what each of these things are, how we did it, and how well we did it, right? So let's start with the first part by addressing the two big questions that scientists always need to be asking themselves, which is, what are we doing and why are we doing it, right? And so this first little bit is going to be dedicated to explaining what exactly parity violation is, how it manifests in the electromagnetic force, and once we understand that, we need to talk about what objects or methods are good for trying to detect parity violation. We are personally using something called the cosmic microwave background, so I'm going to go into a little bit of detail of what that is, and then I'll describe the unique signatures that parity violation does in the CMB. Once we understand that, we could talk about how we actually go about trying to measure parity violation in the CMB. All right, so what is parity violation? In the physics world, parity violation has a specific definition, which is the equations that describe a physical system are not the same under mirror inversion. So the very simplistic example I have here is an apple falling from a tree, and the principle is that the laws or constants of nature that might determine, say, the velocity or the acceleration of this apple, when all other parameters are the same but just mirrored spatially, might be different. Right? So naturally, we have to ask ourselves, if parity is violating in EM, what might that look like? So to answer that question, I have to teach you a little bit about how light works. So light, or photons, are a consequence of the electromagnetic force. Specifically, they're a propagation of electric and magnetic fields, and we typically describe a single photon by the amplitude and direction of the electric field here. So we call the E field direction its polarization, and in this case, it's going up and down. It is linearly polarized because it's going up and down in a straight line. In addition, to going up and down, it can go left and right. And a neat thing about light is that it can be a superposition, meaning that they can be in the same place at the same time, and you can add them together to create new photons. And it's the phasing of these light particles together that can, when you add them together to create a new photon, will tell you the polarization of it. So in context of what we're doing, specifically, you can add two photons in such a way that it creates another photon that is going in a circle called circularly polarized light. right? And so it spins in a circle as it's moving forward. And the exact opposite is true, where you can take a circularly polarized photon going in, say, counterclockwise, and then you can take another circularly polarized photon going clockwise, add them together to create this linearly polarized photon going up and down. And it's the point at which these two photons meet that is determining the polarization of light. Now, why do we need to know this? The reason why we need to know that is like the way that we make EM parity, a way that we make EM parity violating is by adding a special term to the electromagnetic Lagrangian, which is the bit of physics that ultimately describes how light propagates. And the result is that the dispersion relation, or the thing that is determining the speed of light, where you have usually omega minus k is equal to 0, and when the speed of light is equal to 1 in this case, it converts into a dispersion relation in which the speed of light actually depends, you've got this plus and minus sign here, depends on the direction of circular polarization, right? And so the phenomenon where the speed of light is dependent on the direction or polarization of light is called birefringence, which is something that occurs naturally when light is propagating through certain materials. So the important distinction here is that this is a special property of space-time itself, and which is why we call it vacuum birefringence or cosmic birefringence. And you'll hear me calling it cosmic birefringence pretty often in this talk. So recall that we've got two circularly polarized photons making a linearly polarized photon, and it's the point at which these two meet that determine the orientation, right? So if we introduce cosmic birefringence, what you're going to get is one of these circularly polarized photons is going to lag behind the other because the speed of light of it is a little bit slower than the other. And so that means they're going to start meeting up at different points, and therefore the orientation of the linear photon is going to rotate as it propagates through space. And the farther or longer that it travels, the more it's going to rotate, right? So as scientists, if we're trying to determine if EM is parity violating, then a way we can do that is by measuring how much, if at all, the linear photon rotates between the point from which it was emitted and the point at which we observe it, right? So now we have to think about how we can go about measuring that sort of effect. So first and foremost, like I said, the farther light travels, the more it's going to rotate. So distance is an obvious consideration. But if we're trying to use objects in space, not every object has just one polarization, so we have to consider the fraction to which the object is polarized, right? Further, we also need to be able to determine if light has been rotated, which requires the knowledge of its orientation at the point of emission, which isn't always easy to do, especially if we're thinking about stuff out in space. So there currently exists a number of different ways that we try and detect cosmic birefringence. The first being here on Earth using laboratory experiments, such as resonant ear cavities. This is the PVLOS instrument. I think I'm pronouncing that right, on the right here. And effectively what they do is they emit a polarized photon, they trap it in a cavity, they bounce it back and forth a couple of billion times before finally measuring the light again. And the really great part of this technique is that because you're in a laboratory experiment, you can get that high precision on the orientation of that photon. The downside is that even with billions of bounces, the distance that light is traveling pales in comparison when looking at stuff in space, right? And for the stuff in space, not the exact opposite is true, but the opposite is typically true. So for instance, we can look at distant galaxies that are super far away, so the amount of rotation that you're going to get before it hits your face is going to be much higher than if you're just bouncing around in a lab on Earth. But the issue really is convincing yourself that you understand what the orientation of the emitted light is, which is going to be dependent on some very complicated modeling. So another thing that we can look at, which is the thing that we look at, called the cosmic microwave background, is the farthest and oldest light in the universe. So that is great for getting that good rotation. Despite its distance, the difference between the rotation you get between the cosmic microwave background and distant galaxies is only about a factor of 2 or so. So the difference there isn't all that great, but the CMB has some really nice properties that make it a great candidate for measurement. Namely, it has a well-characterized polarization signal, and in the presence of cosmic birefringence, you would get a really unique signature in CMB data, which is really awesome. So we're going to be using the CMB in order to try and make this constraint. So in order to talk about the CMB, in order to do that, I need to give you a little bit of background on what the CMB is. So the CMB is the remnant signal of the primordial plasma that made up the universe shortly after the Big Bang, which ultimately condensed into all of the things that we know of today. Light from the CMB is actually very smooth because that primordial plasma was quite nearly the same temperature in every direction we look. It's not perfectly smooth though, so when we subtract that average temperature, we see all of the clumping or anisotropy everywhere we look. So, and this is the result of tiny quantum mechanical perturbations, which ultimately resulted in slight over and under densities in the primordial plasma, and then it shows up on this in this map as like little warmer spots and slightly colder spots, right? So, in terms of polarization, since that's the thing that we care about, polarization is created in the CMB by one for sure and a couple of other different sort of phenomena, but we're going to talk about two today. The first polarization anisotropy signal is created by the fact that we've got some density anisotropy, as I mentioned before. And recall that the CMB is this hot mess of primordial plasma, so we've got this soup of protons, electrons, and photons bouncing all over the place. Well, when that happens, you get something called Thomson scattering, where when a photon comes in, remember that a photon is an oscillating electromagnetic field and passes through an electron, which has a negative electric charge, which is going to wiggle that electron a little bit, and it's going to redirect some of that electromagnetic energy in the form of another photon in another direction, right? So the result is that if you're staring at the CMB, you're going to get some radiation from photons going left and right and up and down, redirected at your face. Now, if the CMB was completely uniform, you had equal amounts going left and right and up and down, then the net polarization would actually be 0. You've got equal number here, equal number here, equal number here, equal number here, right? However, since the universe is not perfectly uniform, as we were just describing, that little bit of temperature anisotropy is going to result in a small fraction of polarization anisotropy. So in the top left diagram here, we've got some CMB with some hot and cold spots going left to right, and the amount of polarization in that orientation getting redirected toward us is going to fluctuate as well, as you can see here. So in addition, there's this other possible source, which is also created through Thomson scattering, except instead of an anisotropy of matter density, it's a background anisotropy of gravitational waves, which stretches and compresses spacetime. So these gravitational waves could come about from something called cosmic inflation, which actually has not been directly measured, but it does help answer some questions about the early universe, and that's pretty much all I'm going to say about it. But the major thing to note is that instead of going up and down and left and right, you get these little crisscrossy patterns, right? So if we take it one step further and include anisotropy going from all directions, for the density perturbations, you get this nice radial sort of figure, kind of like spokes on a bicycle wheel. And for the gravitational wave anisotropy, you get these sort of pinwheel patterns. And so for the density waves, you get, we called them E mode polarization, and for the gravitational waves, we call them B mode polarization, right? So we now have 3 different anisotropies that we want to talk about, and so we need a way of actually describing it mathematically, and the way we do that is through something called a power spectrum. So this here is a little bit of CMB, and what we can do is we can break down the anisotropy in the CMB on a plot. So on the left here, this is called a power spectrum, and on the left here, we're describing big clumpy things, and on the right here, we're describing the smaller bumps here. And on the y-axis, or the vertical axis here, it's telling you how bright those bumps are, right? So what does a power spectrum actually look like? So this is all of the most prominent power spectra to date, and you're going to see these things called TT, EE, and BB. So we have temperature, E mode, and B mode power spectra. Now, the thing to know is that when we take a power spectra, we're actually doing it between 2 maps, right? So we're taking, when we want to understand the anisotropy in a map, we compare that map to itself. And so you have the TT power spectra. This is the E mode, auto spectra, sorry. This is the E mode auto spectra. This is the B mode auto spectra. And so you can see that the temperature anisotropies are orders of magnitude brighter. This vertical scale is logarithmic. Orders of magnitude brighter than the EE, and higher still for BB. And note that I was just saying that we haven't actually detected B modes. Well, we are seeing B modes here, but they're not primordial B modes from the CMB. This is something else, which I'll talk about in the long future. But another important to note here is when we compare 2 different maps in a power spectra, we call that the cross spectra. And that is telling you about how 2 different maps correlate with each other, how those power spectra correlate. And so now we're looking at TE. And like I was saying, the temperature sources E mode polarization. So you're going to get some correlation in the power spectra in the cross spectra in TE. Now, this is an important note for what we're trying to get to this whole time, which is how does cosmic birefringence affect the CMB? Well, we were just saying that there are no B modes and there are only E modes. So in the presence of cosmic birefringence, you're going to get a linear rotation of polarization. And those E modes are going to get slightly rotated into B modes, and those B modes would get slightly rotated into E modes and vice versa until at some point your E modes look entirely like B modes and your B modes look entirely like E modes, right? So when we take the cross correlation between those two, when we actually do the cross spectra, so we've got E here, E is converted for different angles that you rotate into. E is converted into B, and then when you take the cross spectra between E modes and B modes, your EB actually creates non-zero EB. And what's really cool is that it's non-zero in a very specific way, which means that you can use the EB power spectrum and model it in order to make it a very sensitive way to detect birefringence signals, right? So how do we go about measuring that sort of thing? Well, with telescopes, of course. If we imagine we've got polarized light coming in from the CMB, rotating as it gets to our faces, and finally being collected by a telescope, we can create a telescope that is actually sensitive to polarized light. And if you imagine that this red line here is the sensitivity of linear polarization of light, then we can see the difference in the angle, and then we would be able to measure the EB power spectrum. Now, the issue is that if you can imagine if we are building an instrument and we don't build it perfectly, and this red line is not perfectly where we think it is, then the angle between these two is going to be slightly off, and we can either lose that birefringence signal or more likely create a false one, right? So not only do we have to measure the power spectrum, it's really important to make sure that we know the orientation of this red line really well, right? So if we think about the history of making these sorts of measurements, there is a rich history of this. And so on this plot, what I'm showing right now is CMB constraints of cosmic birefringence dating all the way back to 2008, starting with the quad measurement at 90 gigahertz. And this plot's a little busy, so I'm going to take a second to talk about it. This large lozenge, as John likes to call them, represents the statistical uncertainty. And then this sort of thinner, lighter bar represents the combination, the quadrature sum of both the statistical and systematic uncertainty. And what this is telling us is that for a long time, there was a huge amount of statistical uncertainty. We were limited by the intrinsic measurement ability of our instruments. But as time went on, it was the instrumental uncertainty that was actually contributing most to our measurements. And you can see that there's actually some point in which it deviates from zero, and we technically have a significant measurement, but we're still not super sure about the level of birefringence because we're dominated mostly by that instrumental uncertainty. Now, as we're entering into this new era, you can see that with Planck, this tiny bar, which represents the intrinsic measurement ability, has gotten way better than the previous instruments. And that's because we entered this new generation of really sensitive telescopes that are giving us this really great constraining power from the CMB, but we're now entirely limited by our ability to calibrate our instruments in order to establish strong constraints on birefringence. And so we can see that with these new measurements, so this is coming from ACT, and these are independent measurements using the public data releases of Planck. We have this nice measurement uncertainty, but the issue from all of these is that the calibration of the instrument is still sort of up in the air. Like there hasn't actually been a strong statement of what the systematic uncertainty has been, and that's why I'm including these little bars here. Right, so and this brings us to the crux of my entire thesis, right? You can see that the angle order on here is on the order of tenths of degree. So the goal of my thesis has been to measure the polarization angles of a CMB telescope using a calibrator in order to search for signals of cosmic birefringence, as we just talked about, in the CMB power spectra, with a total precision of both statistical and systematic uncertainty of less than 1/10 of a degree. And so the way I'm going to do this is I'm going to first talk about the telescope, and then I'll talk about the calibrator that we used, and then I'll talk about the analysis, the calibration analysis, effectively how we observe a telescope and get angles out of it. I'll talk about those angles that we got, and then we need to talk about CMB data and how we fold those angles into the CMB analysis. And then I will finish up with conclusions, describing the lessons we learned and the friends we made along the way. Right. So I'm going to take a drink of water real quick. That's a lot of talking. 20 minutes, great. Cool. All right, so talking about the telescope. What is BICEP 3? Well, BICEP 3 is a microwave refracting telescope built and operated by the BICEP Keck collaboration. It observes the CMB at 95 gigahertz. It is a small aperture. It has a small aperture to probe degree scale CMB structure. It is sensitive to linear polarization. That's a big one that we were talking about. And it's located at the South Pole. Now, all of these things make it were designed specifically for its primary goal to detect cosmic inflation, which I totally glossed over. I apologize for that. But that also makes it it checks the box for being a sensitive CMB instrument that is sensitive to linear polarization. And with just a bit of effort, we can also make it sensitive to birefringent signals. So what I'm going to do is I'm going to try and blast through the description of the instrument in order to, help everybody understand what is important about the instrument so we can get to the calibration and so on. All right, so this is a very busy plot of the telescope itself, but what I really wanted to show is that our telescope is actually kind of similar to what you're used to seeing in optical telescopes. It's a refractor, so that means we have an objective lens here, we have a field lens here, here's our camera. Now a significant difference, not the only difference, of course there's many, but a significant difference is that we're trying to observe the CMB, which is at roughly 3 Kelvin, 3 degrees above absolute zero, so we want the CMB to be really bright compared to our instrument, to our camera. So we cool it down to roughly 4 Kelvin with a pulse tube cryocooler, and then for the camera itself, we cool it down even farther to about 1/4 of a Kelvin. Or 1/4 of a degree above absolute zero. Now the camera itself is actually made up of a bunch of tiny little individual detector modules. So each tile is broken up, and it's not one giant monolithic thing like you often see in like CCDs. The cool thing about this design is that if one tile goes bad, or if you've made a better performing one, you can always swap it out for another. So if we zoom in onto one of these tiles, you can actually see that it's made up of an array of a bunch of microwave sensitive detectors, and not just one detector, 2 detectors. So each little blip here is a detector is a detector element. If we zoom in further, we can see why there's 2 detectors, right? So there's this huge array of wires going up and down and left and right, kind of hard to see, but you've got your 2 detector elements here. And if we zoom in further, we can see that each of those little wires is oriented up and down or left and right. So all of the vertical wires go to one detector and all of the horizontal wires go to another detector. And what that means is that we're simultaneously measuring vertical and horizontal polarization, right? And the nice thing about this as well, and notice that the reason why we have all of these wires that are on top of each other is because we want both detectors looking into the same part on the sky. And the way that we do that is, in addition to having these overlapping arrays of antennas, our optics also redirect all of the light onto a single point. So our focal plane or camera is just that, a plane, right? So our optics convert a lateral translation on our focal plane into a direction on the sky, right? And all of that together produces an array of detectors with each with their own polarization, going going vertically or horizontally, sorry. And then it produces a field of view on the sky, so you're sampling a bunch of the CMB at multiple different, at 2 orthogonal polarizations. And then in addition, you can also just rotate the entire focal plane in order to decompose the different polarizations that is on the sky, right? So that was the instrument. Now we need to talk about how we actually go about characterizing the performance, right? So there's a couple of different ways that you can calibrate an instrument. So we have, I've broken it up into 2 different parts. There's either celestial calibrators or ground-based calibrators. Celestial calibrators are, such as the Crab Nebula or the Moon. They're both polarized. What's nice about them is that they're free, TM, or asterisk, I guess, in that, you can just observe them. You do have to take the time to observe them, obviously, but you don't have to do anything extra to actually observe them. The other nice thing is that there's many different types, and what's really nice about that is you can observe them in if they're slightly different, you can observe them differently, and that's going to give you a lot of information on your systematics. You can do cross checks between them two. So if you see information that agrees between the two, then that's a nice cross check. So the disadvantage is that you're ultimately at the mercy of whatever nature gives you, right? So the Crab Nebula for us, actually, since we're at the South Pole, is below the horizon. There are other calibrators that we could use, but that is one thing, right? They are also usually large on the sky. So for instance, even with our telescope that has a relatively low resolution, the moon is actually still kind of blobby for us, and that's that makes it difficult. That adds some complexity to our analysis. And as I mentioned before, which is a big problem, it's difficult to know what the polarization orientation is a priori, right? So for ground-based calibrators, what's really nice about these is that they're customizable, right? You have all the parts, you can customize them to whatever you want, to the specifications of your instrument. They are easier to characterize because you can bring it into a lab, and as I'll describe later, they're very useful. It's very nice to be able to characterize them. And because you've built them to the specifications of your instrument, they ultimately give you better performance. I mean, if you're building it, it better perform better. The disadvantage is that it costs money, which is kind of the bane of scientists' existence. And then there is this issue of different observing observations. Like I said, it's a ground-based calibrator, and we are building instruments that look up into the sky. So fundamentally, unless you have specifically designed your instrument to be able to look at the sky or look at the ground in the same way that it looks up at the sky, there's always this question of whether or not the differences, the different configuration in which you're looking at your calibrator can easily be transferred into your analysis of your sky data, right? So the way we characterize BICEP 3, as I just mentioned, we actually have built it specifically to look at the sky, and BICEP 3 cannot bend down low enough to look at objects on the horizon. So what we do is we install this large flat mirror that redirects the view onto the horizon, kind of like a periscope, and we put our calibrators on top of these nice tall towers to get them a little bit above the ground. And for those of you who are interested in radio, the aperture of the telescope is actually large enough that it's small enough that the far field of BICEP 3 is actually roughly 170 meters, and we place our calibrators at roughly 200, which puts us squarely in the far field, which means that you can convince yourself that the way in which you're looking at your source or at your calibrator is effectively at infinity, at the same distance as the CMB, for all intents and purposes, right? So we've talked about the instrument, we talked about how we calibrate the instrument, now we need to talk about the calibrator itself. So what I'm going to do is I'm going to talk about our calibrator and then go into the observation analysis and then talk about the results. Right? So the calibrator that we're using is called a rotating polarized source, or RPS, and what it does, it consists of a broad spectrum noise source, which is at 95 gigahertz. Note that 95 gigahertz was the observing band of BICEP 3, and it is attached to a rotation stage. And I can show you how it actually rotates. So what it does, this rotation stage takes the entire source and rotates it about its axis. There's a wire grid polarizer in front of the source, which polarizes the light coming out of that source. And then we have a tilt meter down here, which is telling you the orientation of those wires with respect to gravity, right? So as I mentioned, the nice thing about having a ground-based calibrator is that you can well characterize it. And so the way that we know the orientation of the source is by calibrating our calibrator. So the top of this of our rotation stage has a surface, and we measure the orientation of the wires with respect to this surface, and then we measure the tilt meter, the orientation of the tilt meter with respect to this surface, and that tells us the orientation of the wires with respect to gravity, right? And I was going to tell you guys how we do it, but I'm going to skip that stuff for time. So, but how we actually observe the source is by, like I said, we put it on top of a mast. So this is the source, we put it on top of a mast. Then we scan back and forth in azimuth, and then we take steps in elevation. So this is the source itself, and this is just the background. This is what a map of it looks like. I don't know if you guys can see it back there, but so this is the source as it's shining at us, and then you actually make out the ground shield of the instrument right here. Here's the building, and this little blobby here is actually the source's light reflecting off of the snow, which I thought was really cool. So what we do, like I said, the RPS itself rotates, right? So the apparent brightness of our source as it goes in and out of alignment of the polarization axis, the polarization sensitive axis of our instrument, is going to change in brightness. So for a given detector, when it's most bright, that means that both the polarization coming out, the polarized light coming out of the RPS, and the polarized sensitive axis of the telescope are perfectly aligned or maximally aligned. And then when they're maximally orthogonal, then you're going to see no signal, right? And we can plot their amplitudes as a function of the rotation, and that gives us what we call a modulation curve. And we can determine the angle of our detectors with respect to the source by looking at this, by fitting an angle out of this modulation curve. And so we took these observations back in late 2021, early 2022, and we effectively, it took a month of us just observing that source over and over again for all 2,000-ish detectors on BICEP 3 at multiple different orientations. And what else did I want to say about this? Yeah, so that was sort of that observation. So the way we actually fit the angles is, like I said, it's the phasing of that modulation curve, right? So if you're, it's the phasing of the modulation curve for when the RPS is at 0 degrees or perfectly aligned with gravity, right? And the issue is that only tells us the angle of the detectors with respect to the source. What we need is a way of transferring that angle onto the CMB, right? So the angle we need to transfer it to the angle with respect to the focal plane, because that's the way that we transfer it onto the CMB. So what we do is we pick an arbitrary reference point on the focal plane and use a pointing model. The issue is that it's a very complex geometry problem, as John likes to say. I love geometry problems, so this is me, having fun. But the important thing to note here is that it's a complex thing that requires requires us to consider many potential sources of systematics. So now we understand how we're measuring those angles. Now let's actually look at the angles. So as I mentioned, this is what the focal plane actually looks like. So it's actually kind of useful to look at angles in this sort of tile-like view. So here are our angles, and here as a function across the entire focal plane. And you can see that some angles, so if you're brighter, if you're closer to yellow, you have an angle of like -2. If you're a little bit darker, you have an angle of -3. And from tile to tile, you can see that the overall angle actually changes, right? And so this is interesting. So if it was totally flat and perfect, then that would tell us one thing. But what's really nice is that it's not perfect, right? So that means that if we measure some non-ideality, we can compare it to some other non-ideality that is also given to us by physical measurements. So what I was able to do was to determine the pointing. So as I mentioned, the optics redirect where your detectors are going to fall onto the sky. And we have some ideal model of what that's going to be based on our designs, and then we can actually measure the CMB, and the CMB is going to be like, well, actually you're pointing over here, not over here. And so we can compare the difference between our ideal pointing and the pointing we get from the CMB to tell us the orientation of the pointing of the tiles, and we can compare that to the polarization axis of our detectors. So here's the comparison of our ideal pointing versus the pointing we get from the CMB, and you can actually see that some of the tiles are a little bit rotated. They're clocked physically. The alignment of them is shifted a little bit. And you can imagine that if you're taking this overall rotation of the tile, you can imagine that the polarization orientation of that tile is going to appropriately rotate. And so what we can do is we can measure the angle at which this is rotated and compare it to the overall polarization axis of our detectors. And we can see that actually they line up really, really well, right? Now, the note is that it's not lined up perfectly, right? So it has a strong correlation, but it's not one-to-one. So what this is telling us that we have this strong physical motivator that is saying, hey, we've actually done something right in our analysis. But this is a relative measurement here, and the absolute offset, which would actually give us our birefringence signal, is different. So this would actually tell us right now that, hey, if we were to go assuming everything ideal about our CMB, about the instrument, and try and back out some angle, we would hope that if, in the absence of birefringence, it would actually match the offset between these two bars, right? But we'll get into that later. So but the important thing to note is that this is a nice physical validation using real data that we're doing something right in our analysis. So, like I said, we considered many different sources of uncertainty, right? And there's a bunch of different types, right? So, we have this physical mechanical rotation stage, and that's contributing its own uncertainty based on, how well it can get to those angles. There's also this complicated pointing model, which is also going to be giving you some uncertainty. And of course, we're plotting these modulation curves as a function of angle, but it's also giving you amplitude, and that amplitude is going to jitter a little bit depending on how stable the source is in brightness or how stable the gain is of your detectors, which is also going to contribute to uncertainty. And so we've run these through the gamut. We've done a lot of in-depth analysis on our uncertainty, and most of them we think are well understood and within nominal limits. Note that, remember, our precision goal was on the order of 1/10 of a degree, and our lower limit right now is actually a little bit lower than that. So our lower limit is pretty good. However, we did find that we were ultimately limited by some difference in the alignment error that we discovered on the benchtop. Now, remember, I was mentioning that one of the nice things about having a ground-based calibrator is that you can bring it into the lab, you can characterize it as much as you want to, and that's exactly what we did. What we wanted to do is we wanted to take our calibrator and put it in in front of something that wasn't bicep 3. And so we took a lot of the spare parts from the RPS and made a little receiver for it. So it has a wire grid, it has a reference surface, it has a tilt meter that's installed on the inside, and the principle was that we can measure the orientation of this grid with respect to gravity the same precision that we can with the RPS. And if we were to back out the exact same angle that we measure from the RPS analysis that we have measured here for this receiver, which we call the Isaac, then that provides a strong cross-check that we understand the end-to-end measurement. The cool thing about this is that you can also sort of perturb the system, right? So you can make the RPS a little bit brighter. You can, try and examine how the calibration of the tilt meter works out. And so what we did here is we actually just changed the alignment of the RPS. So from pointing directly at the Isaac to pointing, more towards the window or pointing more towards the camera. And what we found is actually that the angle that we back out is very sensitive to that alignment offset, right? So note that this is an alignment offset of roughly like 1 degree, and our angle error is actually going down to about 0.3 over here. And when we did this measurement at the South Pole, I established some priors. I knew, there is going to be some sensitivity to our alignment based off of some geometric modeling that I had already done. And so my priors on that alignment are about 1 degree, and according to my modeling, it was totally fine. But when we actually measured it in the lab, we're getting now this angle of 0.3 degrees, right? Which is kind of alarming. However, the interesting thing here is that I had already mentioned that one of the downsides of observing a ground-based calibrator is that there's always this question of how you're going to transfer this observation of something on the ground to something in space. Well, the exact same thing applies here. We're observing the RPS out in the harsh Antarctic environment. It's on top of a mast. And here, for this measurement, we're measuring these things on the ground that's surrounded by a bunch of reflective metal. This isn't exactly, it doesn't have the same sort of sensitivity. It might have different properties from bicep. So there is still this question that we haven't figured out yet of, is this, if I go this way, there we go. Is this pattern a reflection of something that is intrinsic to the RPS itself, or is it something that is intrinsic to this measurement that we're doing on the benchtop, right? So that's kind of hard to characterize, and that's currently where we're at. But unfortunately, because we don't know, we can't say for certain one way or the other, and so this is what's ultimately limiting our ability to provide birefringence constraints right now, right? So a little bit of a bummer, but there are some really cool things that we were able to back out of this measurement as well. So for statistical uncertainty, the intrinsic uncertainty of the measurement, saying, if there were no systematics whatsoever, you did everything perfectly, everything is awesome, and you're only limited by the intrinsic noise of your instrument, how well could you do, right? So for the RPS bicep measurement, we're actually able to get down to about 0.02, which is 5 times lower than the precision goal that we were aiming for, right? And then on the benchtop, it got even better, right? So because we're not in the Antarctic environment, maybe the gain of the detectors on bicep is a little bit different. We're actually able to get down to 0.006, which is, it turns out to be the intrinsic mechanical uncertainty of the rotation stage itself. So this is telling us that once we figure out all of the systematics, this calibration technique is going to be a pretty solid technique for many years to come for different, as we continue trying to nail down this constraint. So good and bad, right? So to summarize it all together, I'm at 40 minutes, goodness me. This is a complex measurement, with a bunch of different challenges. We have considered many different sources of uncertainty. Most of them are good. There is this large remaining systematic uncertainty from empirical measurements. However, we have this intrinsic repeatability that is really good. And I'm including this last bit here because it's going to help us follow up into the CMB analysis. We have some physical validation from other data that is telling us that there are bits of our analysis that we're doing really well. So the next question is, how do we apply this analysis? We've got our angles. How do we transfer them into the CMB? All right. So for the CMB analysis, I'm going to talk about what I'm going to do is I'm going to go through a similar consistency test that we did in the previous section. And while I'm doing that, I'm going to demonstrate how we actually create CMB maps, go into power spectra, and then fit an angle out of that. Right? And then I'll follow up with another validation study. And as I mentioned before, we're currently being limited by that systematic uncertainty. So we're actually choosing not to look at our birefringence angle right now. And so what we're going to do, just to show that we can do it, is we're going to do a mock birefringence constraint using a CMB simulation instead of that. I'm going to be using CMB simulations throughout all of this. And I'm going to kind of gloss over the details until we get to here, because an important part of the CMB simulations is that they give you a lot of information on the uncertainties that are going into your that are coming from your CMB analysis. So I'm going to talk about it here and then talk about how they contribute to our error budget, and then finally I'll finish off with our conclusions. All right. So as I mentioned, we have this tile plot of all of the angles that we have, right? So what we can do is we can use real CMB data to help boost our confidence in the analysis without actually looking at that birefringence angle, because right now we're limited by that uncertainty. So we're going to make simulations of the CMB that reflect exactly what our data is doing, but we're putting in our own expectations of what the angle should be, and then compare that to real CMB data in a way that keeps us blind to the birefringence angle until we're actually ready to look at it. And the way we're going to do that is we're going to break up the data based on the detectors and what their angles are, and then we're going to subtract them from each other. Right? So, like I said, we're going to break up these angles. So we'll break them up in the thirds, where the upper third has the more yellow ones, the middle third has these middling ones, and the lower third has the -3-ish detectors, right? And then we're going to take only those detectors and make CMB maps with them. But these are simulated data. But the way we make CMB maps is by observing, every single year, all year, we observed this single patch of sky to get us some really deep CMB maps. And then for a single detector, we scan across the sky. And then as we scan across the sky, we develop more of this map. And then we rotate the entire focal plane to a different, what we call boresight angle. And we observe other parts of the sky. And then over an entire year, we can co-add all of that stuff together to make this map for a single detector. Now we have many detectors for a single subset, so we add these together to make our CMB maps, right? And so and we have three, right? So we have temperature here, which I was talking about before, and then we have two polarization maps. So you can convert these into E and B, but right now I'm just showing another composition in Stokes Q and U, and then for right now, for demonstration purposes, I'm just showing you Q here, right? So we now have our CMB maps. How do we convert those into power spectra? Well, effectively what we do is we just take a Fourier transform. So we Fourier transform these maps to turn it into a Fourier space, and where the positive here is the real values and the negative here is the imaginary values. And I don't know if it's easy for you guys to see, but there's these rings, these concentric rings that are going out and out and out. And the way we convert these into power spectra is just by taking this Fourier transform and then taking the azimuthal average on one of these rings in order to calculate our power spectra. Excuse me. And so this is, we have a number of different power spectra. We have T, we have E, we have B, which will give you 6 different combinations. So right now I'm only showing EB because this is the one we care about for our birefringence signal. And now you can see, if you remember what that signal looked like, it dips down a little bit. And for here, this is our lower angle, this is our middling angle, and it dips way down for our lowest angle, right? So now we need to fit angles out of these power spectra. And the way we do that is we come up with this nice model, right? And like I said, because it rotates in a very predictable way, we can come up with this nice simple model for it. Now, as I mentioned, like we're simulating CMB data, so BB is effectively 0. So what we're really doing is we're taking the E modes and we're multiplying it by this value, but since our angle is typically really small now, we're dealing with tenths of a degree, it effectively comes out to multiplying it just by some scaling factor, and that's how you get this nice thing. So you can see here if we're negative, then these are going to dip down in such a way like that, right? So if we're at 500, we have 500 here, and it dips down, right? So now we can fit angles out of these. And this is transferring into angles. And I'm realizing that I didn't tell you what these little gray lines are. So when I was showing you CMB maps, I was showing you just one realization, one simulation, and we actually can compute 50 of them. So this is, so each of these gray lines is one of the 50 simulations, and then this black line is the average of those, right? So you can see we're taking these and converting them into angles, and you get this nice distribution of angles, and this black line is just the average of those two. And so we have this input angle, which is the angles that we had broken up into subsets, and then we fit an angle from the power spectra. And now this one is for sure a linear line, right? You could see that if we put in 1 degree, minus 1 degree, we're going to get out minus 1 degree, which is really, really cool, right? So this is a validation that for our simulations, we can put in whatever angle we want, whether we consider it a miscalibration angle of the instrument or a birefringence angle that we're just sort of injecting. We can get whatever angle we want out of that, which gives us confidence that if there is some sort of celestial signal out there, we can accurately back it out. Which is really cool. So what we're going to do, though, is we don't want to know actually what the absolute values are. So we're going to subtract this one from that one, we're going to subtract that one from that one, and then we're going to subtract that one from that one to tell us the distance between the two, but not tell us the absolute value. And that's effectively what we're doing here, right? So what you're going to do is now you just have this distance. And now what we're going to do is we're going to do the exact same process with CMB data, with real CMB data, but we're just going to skip all of the stuff. We're going to make our maps, but not look at the power spectra. We're not looking at angles. We're going to go directly to computing everything blindly and then subtracting them and plotting them on the same plot. Now, if the real data agreed with the simulation data, that expectation, then these are going to overlap. And look, they do. Hey, hooray. So this is really good. What this is telling us is that we have real data is matching predictions from the simulations. Now, the issue is that it's only relative angles, right? This isn't telling us the absolute birefringence angle because we're still being hidden from until our uncertainties are resolved. But we have yet another nice validation using real data that is telling us that we're doing something in our analysis correctly, which is cool. All right, so I'm going to change gears and I'm going to backtrack a little bit to talk about CMB simulations. The nice thing about CMB simulations is that we have constructed them in order to capture the complexity and all of the uncertainty involved in our instrument, in the CMB maps. And what's nice about that is, like, not only will it allow you to create predictions when you're trying to test the analysis, but it also tells you about the uncertainty that is going to be folded into your ultimate constraints on anything, not just birefringence. Right? So we have a couple of different types of CMB simulations. We have just good old CMB, which is lens lambda CDM only. It's just basic stuff. And then there is a bunch of stuff between us and the CMB that is big and bulky and gravitationally lenses the CMB, and then which is going to contribute its own sort of leakage between E modes and B modes. And then we've got galactic dust. We're sitting in a galaxy. There's dust. It also has its own signature. And then, of course, there's the instrumental noise, right? So we're measuring it with an instrument. I don't think I've mentioned this before, but we're only measuring it with 2 years of data. And this is supposed to accurately capture all of the noise that is contained in our instrument. And then, of course, we're going to do various combinations of these. But what's nice is that we can fit angles to power spectra in order of each of these individually in order to determine how each of these components contributes to the total uncertainty of our birefringence measurement as it's contributing from our CMB analysis. So right now we're currently dominated by noise, right? So if we're at 0.078, we're currently dominated by noise here. But the cool thing about noise is that you effectively, if everything goes right, you could just add more years to get that noise down, right? As you integrate over time, your noise, the contribution from your noise is going to go down over as root n. And what I've been able to calculate is that we're only using 2 years. We're using 2017 and 2018 CMB data. If we include all the way up to year 2023, it's going to be comparable to our next limiting factor, which is lens lambda CDM, which effectively comes out to a 50% overall improvement just by including the CMB data that we have already, right? Which is really, really cool. Now, the issue is that then we're next going to be limited by gravitational lensing, which does not go away. The galaxies are always going to be there. The more you integrate, it doesn't go down. So we're actually going to need to integrate a sort of different approach, which is going to require delensing the CMB in order to push this down even farther than what we're currently at, right? So that's our uncertainty. The cool thing about uncertainty is when you combine them all together, it tells you the significance of your measurement. And so like I said, we're not able to unblind to the real birefringent signal right now, but to show that we're actually capable of doing it, I'm using a single simulation in lieu of real data in order to just to demonstrate that we can do it, right? So I've taken a single sim, and in the red lines here is what that simulation is. And of course, because it's a simulation, it falls nicely into this little, along the rest of the simulations. And then we'll fit angles to them, and we'll plot that, that angle that we get out of it over the distribution of the sims, except these black bars here are actually the combination of both the uncertainty from the CMB you get from scattering all of the different simulations, and the instrumental analysis, which is what we've got right here. So what this is actually telling you is that combined with the instrumental analysis and your CMB analysis, this will give you the significance of that detection, right? So if this falls well beyond out here, this would tell you like, hey, you're probably detecting something. And whether or not it's actually new physics would require a bit more consideration, but that's that, right? So how do we compare to previous effort? Now, we haven't actually unblinded. We don't have a proper constraint yet, but I did want to put this plot here to show where we're at, right? So even with the intrinsic measurement uncertainty, we're actually doing a little bit better. We're actually comparable to everybody else, but if everything goes right and it turns out that uncertainty doesn't actually correspond to something that is intrinsic to our calibrator, then our total uncertainty is going to be amazing. But even if it turns out that it's not all that great and we have to include this additional uncertainty, it's actually still pretty competitive, all things considered, right? But that just means that we're going to have some more room for improvement. So that's currently our current area of active investigation, but there's plenty of more stuff that we can do. So pretty cool. Now, in conclusion, we attempted to constrain cosmic birefringence with BICEP 3 using a rotating polarized source. We were ultimately limited by our calibration systematics. But we do have proof of high measurement repeatability, and we have a couple of different validating tests that we've done using real data that tell us that we're doing something, that we're doing things right. And for future work, of course, we're going to continue working on the current analysis, and but we can also just repeat that calibration. We have plenty of ideas of how we can make this measurement better already. Different hardware upgrades, observing strategies, and so on and so forth. And then, of course, we've measured these angles, but we've always been assuming their ideal values. So when we apply this to other analyses, we can actually calculate how that difference in assumption is going to contribute to your systematics and other analyses. For instance, the primary goal of biceps, computing of the tensor to scalar ratio, right? And then, of course, we are measuring the CMB, and we're trying to establish an absolute reference of the CMB. So we use our calibrator to establish an absolute reference for a telescope. The telescope is going to tell us the orientation of the CMB, and everybody observes the same CMB. So what we could do is we can create a CMB map that everybody could use as a calibration standard. So that's another thing that we're considering, right? Yeah, so that is my thesis in a nutshell. I just want to thank everybody. This is when we actually went and made the measurement back in 2021, 22. It was really awesome. During COVID times, we weren't able to send a whole lot of people out there. So I was one of the few lucky people that got to go. This is Calvin Tsai. I think Calvin Tsai is right there. Yeah, so it's been a wonderful time. Met a lot of good friends. We learned a lot of lessons. So thank you so much.
Okay, great. And you finished before the hour. We definitely have time for a few questions. If people do need to leave, that's totally fine. But let's take a few questions from the audience or from folks online. You can type them into the chat.
Great talk.
Thank you.
Thanks, James. That was wonderful. Yeah, but I was wondering about the effect itself, which you're trying to measure. It's kind of rotation of this linear polarization angle, which can come just from normal Faraday rotation, right? So, first job is to say that the universe could not have produced it through just plasma processes. Is that a trivial thing, or do we know enough about the universe and the magnetic field to say this? What if we did measure something that it is not due to just?
Yeah, that's a wonderful question, and I think the approach to that. So, as I mentioned, all of this is at 95 gigahertz, right? So the next step would be like, if we actually detected something, we'd be like, all right, well, maybe we've detected something, but it's only at 95 gigahertz, so it could be birefringence, it could be primordial magnetic fields or something. So what we would have to do is we would have to do follow-up measurements at different frequencies. Then if it's Faraday rotation is frequency dependent, so we can say like, well, that would actually tell us, it would help us probe the parameter space of actually what that effect is, right? So and vice versa, I think. So wonderful question.
But meanwhile, you actually have now an upper limit on primordial magnetic fields. Is it interesting?
That is a good. I think we do. Yeah. Well, a lot of the nice thing about this is there's many experiments observing at different frequencies, and all of them have established upper limits. None of them have made a detection, and so I think that's ultimately to answer your question. Yeah, I think it's on the order of certainly less than a third of a degree, especially with Planck. Planck measures at a bunch of different frequencies, and so there's been a multi-frequency analysis down to a third of a degree, I think. Yeah. Thanks very much.
Yeah, because I never get to ask you any questions.
Yeah, I'm a little scared.
I don't think you're going to have any trouble answering this. I was just wondering, in your model, you include dust but not polarized synchrotron emission, and is that just completely negligible at 95 gigahertz, or is there another reason?
That is a good question, and I don't think I know the answer to it. Synchrotron would be polarized, right? But what signal it produces in EB, so there is this. There's currently this assumption that there's going to be no EB or EB signature coming from dust. I imagine that would be the same for synchrotron, but the synchrotron signal is very low, right? So I don't actually know the answer to that question, but it's actually probably something worth looking into, because we look at dust, right? Yeah, not sure.
Have you considered cosmic variability, all the background AGN that are in your field, that you are repeatedly using the same piece of sky, right? I think that's what you've told us.
Right.
It isn't it isn't constant. It's fluctuating.
Yeah.
And to what extent has that been considered, or is it likely to be negligible in terms of polarization effects?
Yeah, so I think the only way in which we have considered, I think we've always assumed that it's static. In terms of the gravitational lensing, of course. Because it's a snapshot, right? Everything moves super slowly. But as far as the amplitudes go, we do we're averaging over many years. So if I would think that transients or something, the variability that is happening on super fast timescales is gonna get washed out. But I think longer term effects might be considered, but I don't know how much that would contribute. Does that answer your question?
Yeah, thank you.
We've got one from online that I'm going to take now. So Professor Bill Holtzapfel from Berkeley asks, is isotropic or anisotropic cosmic birefringence more theoretically motivated? How do the current limits on these two types of measurements compare?
Oh, that is a great question. So the anisotropic birefringence, so there's a couple of different ways that you can source birefringence. One is through just a constant of nature. The other is actually through coupling of photons with these things called axion-like particles. And neither of these things, like one could say that, either of these things are, or whether or not they're motivated or well motivated, but it's the axion-like particles that would actually source anisotropic birefringence in addition to isotropic birefringence, which I am looking at and actually didn't mention the difference in. Because anisotropic birefringence is a relative measurement, you're not actually caring about the absolute overall rotation. You're only worried about how things differ between each other. I think the constraining power for anisotropic birefringence is actually much higher. But they are, it's all through this, this model of axion-like particles, and I think they are probing different sort of properties of axions. I'll admit that my knowledge is not that deep in that respect, but I do think that the constraints through anisotropic birefringence is going to inherently be higher. Yeah.
I'll ask a simple follow-up question for that one. Can you name one experiment that's published some constraints
we have.
on
we've actually done a
anisotropic
number.
birefringence?
Yes, so we've actually done
perhaps time variable birefringence as well.
That's right. Yeah. So we've actually established constraints on both spatially varying birefringence, where if you look up in this part of the sky or this part of the sky, does that angle actually change? We've also we've been measuring the CMB for years now. So we've also done an analysis of time varying birefringence, where on whatever time scales that we've been able to look at them, and we have established upper limits, but no proper detections.
We had, and maybe we can have one more question after this one before we wrap up.
Hi. Can you go to your beautiful tile plot of the angles, green and blue colored?
Yeah. Hold on.
Yeah, that.
This one.
Yes.
Yes.
I think you said that these, like especially the module-to-module effects, those are probably most likely due to how they're physically clocked in there. Yep. Is that right? Okay. So my question is, should we be trying to improve how they are physically installed to reduce this, or does it not matter, and more what matters is your ability to physically measure that clocking?
Now that is a good question. I mean, all of these have been good questions, but this is one that Claire and I have been thinking about in the past 5 minutes. So, so to answer your question, we actually don't know, and that is something that is we're currently investigating. Clara actually is trying to determine the delta R, the amount of bias you would get on the tensor to scalar ratio if you're assuming ideal, but the angles are actually have this tile to tile variation in angle. So we don't know yet, but it's looking like it's going to be negligible, but those results aren't out yet.
Thank you. Great talk.
Claire's moving her head. I'm not going to say which direction. Thanks, Tyler.
Any more questions before we wrap up? Okay, let's thank James one more time.
Thank you.